Hey guys, I have your notes pulled up for section 3 for day 1, and up at the top, we're going to be talking about velocity as a rate of change and other types of rates of change. Keep in mind that back in chapter 2, I started you on average rate of change using 2 points. It's just slope. And instantaneous rate of change, that's where we move the 2 points closer together. So as the distance between them approaches 0, instantaneous rate of change. Remember, this is derivative. So you're going to hear the words, find the rate of change today, and unless it specifies that it's average, like from x equals this to x equals this, then we're referring to instantaneous rate of change. Wanted to remind you a little bit about notation before we get started. If you have a function named y and x is your variable, when you do the derivative, you're going to call it the derivative of y with respect to x. It means the derivative of y and x is my variable. So for number 1, part A, find the rate of change of the area of a circle with respect to R. So find the rate of change of A with respect to R. You need to recognize it's asking for instantaneous rate of change, derivative. Those phrases have to be stuck together in your head. Find the derivative of area with respect to R. Well, the first thing we're going to need is an area equation to do our derivative on. So, for part A, our basic area equation for a circle is pi r squared. And part A is asking us to do this. So as I look at this, I have to keep in mind R is my variable. R is what I can do the power rule on. What is pi? Pi is just a constant. Pi is 3.1415926, blah, 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 out in front of R squared. Okay, so pi is just a constant. R is my variable. I'm going to do the power rule on R, and I get 2 out in front. The pi is still there. I get R to the first. So this is the derivative of area with respect to R. Part B. Evaluate this. Evaluate the rate of change when R is 5 and R is 10. Now, that is super easy for you. You're just going to plug in 5, you're going to plug in 10. What you need me for is to show you how to write it. So, because remember, you're not going to put random math on your paper. So, I should not see this. Plug in 5. 10 pi, comma, 25. Nope, that is random math on your paper, and that is not acceptable. So, when you're substituting in a number for R and it's written in this form, you're not going to like it, but this is how we're going to do it. I'm going to say I'm using the derivative and I'm plugging in 5. So I'm going to do vertical bar, and down here, R equals 5. If this were a function named f, I could do this. But it's different. This is different notation. So I have to note it differently that I'm plugging in 5. I know, it's more writing. I know, you don't like it. Get over it. So I plug in 5 and I get 2 times 5, I get 10 pi. And I also need to do dA, dr, evaluated at R equals 10. It's 20 pi. Okay. Did that. What are are the units for dA dr? Just so you realize what we're dealing with here, this is just like slope. It's just like changing my y values over changing my x values over, except now I'm looking at changing my a values over changing my r values. And I hope that you all are okay. I'm surely in science classes you've used enough delta for you to understand that that means the change in and the change in. So, if I am measuring the change in area, what are my units for area? Let's see. Inches. Okay, so it's going to be, the top is going to be measured in square inches. The bottom, how does the radius change? Well, a radius is just a linear measurement, so it's just measured in inches. Now, you might be tempted to cancel one of your inches, but we're not going to do that because each of them has a really important meaning. And so I can say the rate of change is so many square inches, referring to area, per inch of radius. Moving right along to page 2. Part A, write the area of an equilateral triangle as a function of side length s. Okay, well, first of all, that's the formula for area of a triangle. Problem with this is not the answer in part A, because this can be the area of an equilateral triangle, but it says as a function of. That means my variable needs to be s for side length. And right now, I only have base and height. So I need to redo this equation so that I have a equals, and that the only variable over here is an s. So I think what I'm going to do is I'm going to come over here and I'm going to draw an equilateral triangle as best as I can. That's not too bad. Hope you can see that. And I can call its side length s. So this is s, this is s, this is s. Degrees, 60 degrees. But wait, I'm going to draw the height of the triangle right here. So that I've split my top angle into 30 and 30. All right, now, this is where you're going to need to think back to geometry. I'm not sure about algebra 2, but pre-cal also, we used special right triangles. You need to have your special right triangles memorized. On a 45, 45, 90, whatever each leg was, we can go 1, 1. The hypotenuse is 1 times the square root of 2. And on a 30, 60, 90, 60, 30, 1, 2, square root of 3. So whatever the length of the leg is, the length could be 7. If this is 7, this is 7, this is 7 times radical 2. On a 30, 60, 90, I call this the short leg because it's across from the 30-degree angle. and it should look shorter than this one, especially if I drew it to scale, which looks like I've done a horrible job. And my projector disproportionate things. That's not the right word. My projector, I don't know. Anyway, so this is going to be the short leg. This is going to be the long leg across from 60. This is the hypotenuse. Whatever the short leg is, the hypotenuse is always double. Whatever the long leg is, whatever the short leg is, the long leg is always that number times radical 3. So in this case, if this short leg were 6, this would be 12. This would be 6 radical 3. Memorize those. Okay, now that I've done that, this height of my equilateral triangle cuts this side length in half. So this measurement down here is 1/2 S. Just from here to here, this is 1/2 S. The hypotenuse is double that, so 1 S. And then my long leg is going to be this times radical 3. So I'm going to do 1/2 times the base of the blue triangle times the height of the blue triangle. The entire base of the blue triangle is S, and the height of the blue triangle is radical 3 over 2 times S. I'll simplify that, and I'll get area equals Now this is the answer to part A. Area in terms of S. Part B. Find dA, ds. That's what part B says. Find the instantaneous rate of change of the area with respect to a side S. So do the derivative on that. This is just a constant. Power rule it. Lower your exponent by 1. Part C. Oh, substitute in 2 and 10. All right, well, got a little bit of writing to do based on the way it's written. Notice my variable is S. That's where I'm plugging in the 2. So I'm going to go dA ds evaluated at S equals 2 is, let's see, plug in 2, the 2's cancel, I get radical 3. Label, so no random math, plugging in 10. I get 5 radical 3. And part D. Remember, this just represents the change in area compared to the change in the side length. Remember, the derivative is just slope as that distance get closer and closer together. So it's just the change in y, in this case A, over the change in x, our variable, in this case s. So how's area measured? Well, area is measured in square units. Side length is measured in linear units, just like that. There we go. Hopefully that was a nice short video, and you can get started on your homework and better understand rates of change.